and denominator, right? So like let's assume that the numerator, like we just show this with the n of s divided by denominator s, right? So it can be 1, it can be any s term, like so like let's just like show gs times ghs like this, right? And we said that the poles of the closed loop system happens at this point, right? So it happens where 1 plus k ns ds is equal to 0. So if we write this, if we simplify this, it means that ds plus kns is equal to 0. Okay, so poles of closed loop system happens when this is satisfied or when this is satisfied. Okay, now if k is equal to 0, if k is equal to 0, the poles of the system happens where ds is equal to 0, right? So the poles of the closed loop system are gonna be exactly the poles of the gs times gh. If k moves to infinity, right? If k moves to infinity, this is gonna be a bigger term, so this is gonna be ignored, and this means that since this is finite, means that n of s has to be equal to 0. Okay, it's a little bit complicated, but look at this part. We're looking at this part. This itself has some zeros and some poles, right? So I have some zeros and some poles. Now we're saying that if k is equal to 0, the poles of ts are gonna be exactly equal to the poles of this thing. And if k moves toward infinity, the poles of this system are the zeros of this system. Okay, so the poles of t of s are gonna be the same as poles of gs times ghs if k is equal to 0. As k moves toward infinity, the poles of ts are gonna be the zeros of gs times ghs. Okay, now just keep this in mind now. So let's look at one example. Just gonna write this is like, keep this in mind, and also remember that if k is equal to 0, poles of closed loop system are poles of gs times ghs. If k moves toward infinity, poles of closed loop system are zeros of gs times ghs. Okay, now let's assume that we have an example. Let's just like work on this example where gs times ghs is given. It's this term s minus 1 s plus 3. Okay, so we have the transfer function of our plant, we have the transfer function of the sensor or measurement unit, and we want to find the poles of the closed loop system. Okay, so this one has a 0 at s equal to 1 and has a pole at s equal to -3. That's what we have. Okay. So first of all, we want to know like how many poles we have for the closed loop system. The closed loop system has a pole, or has like poles when 1 plus ks times GHS equals 0, right? Because this was in the denominator. Let's just write that down. 1 plus k times s minus 1 s plus 3 equals to 0. If I simplify this, s plus 3 plus ks minus k equal to 0. So it means that s times 1 plus k plus 3 minus k is equal to 0. This is just like a linear equation, right? So it has only one pole, just like the order of the equation is 1. So it has only one pole. So we know that our closed loop system has only one loop. One pole. We also know that at that pole, these are satisfied. Okay. And we want to know how change of k would move this pole. So like how this pole is gonna move as k changes. That's the basic application of Routh-Lucas. We want to see for different values of k where that closed loop pole is gonna be. Okay, so first let's locate the pole and 0 of this term. So this is the s-plane, this is real, this is imaginary. So we know that the pole, it's gonna be at s equal to -3, and the 0, it's gonna be here. Okay. So pole, there's only one pole for the closed loop transfer function, right? And it's gonna be somewhere on this plane, right? But as k changes, that pole, it's gonna move. But we know two things here. We know that the poles of closed loop are exactly the poles of GSHS when k is equal to 0. So here, as k is equal to 0, when k is equal to 0, the poles of